Thank you very much for the invitation. It's a real honor to be here. I'm going to, okay, so some of this might be review for some people, but hopefully I still say something interesting. So I'm going to start with the Theorem of Gromoff to sort of motivate the work that I'll do in this talk. And so this theorem is from 2014, and it says the following. Let M be a smooth manifold and kappa from M to R a continuous function. And suppose that we're in the following situation. So we have a sequence of, these are C2 Riemannian metrics GI that are converging uniformly to some limiting metric G. And so here we're going to suppose that we know that the limit is smooth. So here we only have uniform convergence, but we're supposing that somehow we also happen to know that this limit is smooth. And then suppose that each metric in the sequence satisfies this following pointwise lower scalar curvature bound. So the scalar curvature bound of each GI at X is bounded below by kappa at X for all X and M. And so then the punchline is that the scalar curvature of this limiting metric G is also going to be bounded below by kappa. All right. So in other words, what this is saying is that pointwise lower scalar curvature bounds are preserved under uniform convergence. So this is kind of surprising. It's surprising because here we only have uniform convergence, and yet somehow, since we only have uniform convergence, we wouldn't really expect to be able to say very much about the scalar curvature of the limit. And yet these lower scalar curvature bounds are preserved. Okay. And so if you wanted to prove this, you could, First I was going to say, so recently there has been another version of this result proved. This is by Ricci Huang and Manchun Li. So it's basically a version of this result, except instead of having this pointwise lower scalar curvature bound, what they have done is replaced this with the condition that, for all small balls around any point, the negative part of the scalar curvature minus kappa goes to 0 in ln over 2. Okay, and then the same conclusion holds. Okay, so this just came out at the end of last year. I think it's on the archive right now. Okay, so anyway, returning to the original theorem of Gromoff, if you wanted to prove this, you could proceed in one of two ways. Okay, so, I'm not an expert on Gromoff's proof, and I'm certainly happy to be corrected about anything related to this, but, my understanding is that basically what he does is he recognizes that these sorts of lower scalar curvature bounds can be understood as kind of a C0 condition, or be understood as, something that is defined only in terms of C0 data. And then, since it has this sort of C0 characterization, naturally this lower scalar curvature bound is preserved under C0 convergence. Okay, and so another way of stating this is that he sort of creates this generalized notion of what it means to have a pointwise lower scalar curvature bound that, only depends on C0 data, so it makes sense for C0 metrics, and then is stable under C0 convergence, and of course agrees with the usual notion of a lower scalar curvature bound for C0 metrics that happen to be C2. Okay, and so, I'm, as I said, not an expert on this type of definition, but basically it has to do with the non-existence of certain types of polyhedra. Okay, so I'll maybe just write like polyhedral to give you a sense of the tools involved here. And so, if you had a generalized notion of a lower scalar curvature bound that satisfied these properties, then the way that you could prove this theorem is as follows. So, you have the metrics in your sequence GI that satisfy some lower scalar curvature bound in the usual sense, which means they also satisfy this lower scalar curvature bound in this sort of generalized C0 sense. But then this generalized C0 notion is preserved under C0 convergence. So the limit is also going to satisfy the lower scalar curvature bound in this generalized C0 sense, but then we also know that the limit is C2. And so it follows that the limit is going to satisfy the classical lower scalar curvature bound. Okay, so this is sort of like a high level explanation of how you would prove this theorem using a sort of generalized C0 notion of lower scalar curvature bounds satisfying these properties. Okay, so that is one way you could prove this theorem. Another way that you could prove this theorem is due to Bandler. And so Bandler uses the Ricci flow to prove this theorem. Okay, and so, we've all just seen what is a Ricci flow, but I will remind you again, a Ricci flow is an evolution equation for Riemannian metrics on a manifold. It's this evolution equation. And then we can prescribe some initial data. And the reason that you might guess that Ricci flow is relevant to this topic, sorry, someone's hammering in the apartment. The reason that you might guess that Ricci flow is relevant to this theorem is that the scalar curvature has this nice property under the Ricci flow, namely that uniform lower scalar curvature bounds are preserved under the Ricci flow. So what I mean by that is that if my initial data G0 satisfy some uniform lower bound, so here kappa naught is a constant, Then for all positive times for which the Ricci flow is defined, each time slice of the Ricci flow is also going to have scalar curvature bounded below by kappa naught. Okay. I'll just say, so like for me, Ricci flows are always called tilde GT, and that's because they're these sort of, they're going to be like non-standard Ricci flows. Okay, so, if we were sort of thinking about this nice fact that uniform lower scalar curvature bounds are preserved under the Ricci flow, then, we might guess that it's possible to prove this theorem of Gromoff in the following way. Okay, so I'm actually going to lie quite a bit here, but maybe this will just give you a general sense of the proof. So what I could do is I could take my, my sequence of metrics, GI, they're converging uniformly to some metric G. And what I could do is I could run the flow to get some GI of T for positive times. And I could also run the flow starting from my limiting metric to get some G of T. And then somehow the flow might turn the uniform convergence of the initial data into locally smooth convergence of the time slices of the flow for positive times. Okay. This is for T greater than 0. And so then, at least in the case of uniform lower bounds, not pointwise lower bounds, I could try to prove this theorem as follows. So, I'm assuming that my GI satisfies some lower scalar curvature bound, and then that lower scalar curvature bound is going to be preserved by the flow. So for all positive times, the GI of T will satisfy that same lower scalar curvature bound. But then since I have locally smooth convergence for positive times, the limiting flow, G of T, is also going to satisfy that lower scalar curvature bound for all positive times. And then I could let T go to 0 to find that this limiting metric G satisfies the lower scalar curvature bound. Okay, so that's how you would prove it. Of course, the reason I said I was lying here is that we know that uniform lower scalar curvature bounds are preserved under Ricci flow. But, this is not a uniform statement. This is a pointwise lower bound. And so it's not true that pointwise lower bounds will be preserved under Ricci flow. So somehow, if you want to prove this theorem using the Ricci flow, you need to figure out some way of localizing the argument that I just said, which is a non-trivial thing to do. But anyway, this is what Bamler does in his 2016 proof. Okay, so we have these two methods for proving the same theorem. We have this sort of generalized polyhedral definition method, and then we have this other method using the Ricci flow. And a priori, these two methods, don't appear to have too much to do with one another. And so this leads us to ask whether there's some, underlying connection between the tools that are used in both of these proofs. Okay, and so this is sort of the jumping off point for me. And so my motivating question is, can Gromoff's polyhedral definition, the C0 lower scalar curvature bound, be reformulated in terms of Ricci flow? Or in other words, is there some way to define, what it means for a C0 metric to have a lower scalar curvature bound using the Ricci flow in such a way that is equivalent to this polyhedron characterization of Gromoff? Okay, let's see, what did I want to say next? Okay, and so, specifically what I was thinking about is that, in the global case, there is a very natural way to define what it means to have a uniform lower scalar curvature bound using Ricci flow. So namely, if I have, some C0 metric and I could somehow start a Ricci flow from that C0 metric, it would be very natural to declare that my C0 metric has non-negative scalar curvature if for all positive times the Ricci flow starting from that metric has non-negative scalar curvature. Okay, so there's a very natural Ricci flow characterization of a C0 lower scalar curvature bound. Did I say using Ricci flow? In the case of a global lower scalar curvature bound. But really, Gromoff's theorem is a theorem about pointwise lower scalar curvature bounds. Okay, and so somehow the subtle thing is, how do you localize this definition? Okay, and so, there's sort of a natural way to localize Gromoff's polyhedral definition. So how should I explain this? So, a way to globally define what it means to have a lower scalar curvature bound, maybe a non-negative uniform lower scalar curvature bound, would be to say that your Riemannian metric has no sort of bad cubes. This is kind of a vague way to say this, but essentially no cubes with strictly mean convex bases and acute dihedral angles. And then a very natural way to localize this would be to say, okay, well, let's declare that we have non-negative scalar curvature at a point X if there is a neighborhood of X that has this property. But somehow it's not really clear how to localize this Ricci flow definition. And in particular, what you would want is some kind of localized definition which, if it is satisfied everywhere for a constant, implies the global definition. And so somehow doing this is a little bit of a subtle thing. And that was, kind of the focus of a lot of my work for this project. Okay. Before I move on, I just wanted to mention that there are some other people who have been doing, other interesting things in this direction. So in 2014, Dan Lee and Philippe Lefloc defined this sort of distributional notion of scalar curvature for metrics in L infinity loc and W12 loc with inverse in L infinity loc. And then more recently, Lam and Simon came up with some sort of L2 notion of non-negative scalar curvature for metrics in W22 and L infinity on closed form manifolds. And they also showed that for initial metrics with non-negative scalar curvature in this sort of L2 sense, you can find a Ricci flow that is going to have non-negative scalar curvature in the usual sense for all positive time slices. And then also more recently, Jiang Sheng and this is Huayu Zhang showed that if you have metrics in W1P, so for here, P is greater than N, I think, and also C0, that have non-negative scalar curvature in the sense of the Lee-Lefloc definition, then also you can find a Ricci flow for these metrics that have non-negative scalar curvature, or I guess scalar curvature bounded below by kappa naught in the classical sense. Okay, so, I think these definitions have a slightly different flavor than what I'm going to talk about today. I'm talking too fast, I can tell. These have a slightly different flavor from what I'm going to talk about today because these involve distributional derivatives. But I just wanted to mention them because there's a lot of interesting work in this direction. Okay, so anyway, so what I would like to do is I would like to figure out whether Gromoff's polyhedral definition of non-negative scalar curvature for C0 metrics can be reformulated in terms of Ricci flow. And this is a hard question. I don't know the answer to this, but one reasonable first step would be to just try to use Ricci flow to come up with a reasonable pointwise notion of a lower scalar curvature bound for C0 metrics. And then later, if it's sort of a nice enough definition, then later, hopefully we could show that it also has this polyhedral characterization. Okay, so that's the goal for this talk, is to develop a reasonable pointwise notion of a lower scalar curvature bound for C0 metrics using the Ricci flow. All right. Okay, and so, such a reasonable definition should satisfy certain items. Okay, so I'm going to briefly summarize these items and then I'll talk about them in a little more detail. So first of all, I want my definition to be stable under greater than second order perturbation of the metric. Second of all, if my definition holds everywhere for a uniform lower bound, and I have some Ricci flow starting from my initial metric, then I want the lower scalar curvature bound to be preserved. So in other words, I want uniform lower bounds to be preserved under Ricci flow. And then last of all, of course, I want my definition to agree with the classical notion of a lower scalar curvature bound if I have a C0 metric, which happens to be C2. Okay, so this first one that I want my definition to be stable under greater than second order perturbation of the metric. What I mean by that is if I have two C0 metrics, G prime and G prime prime, such that G prime of X minus G prime prime of X is bounded by the distance raised to some power greater than 2 from X to X naught for all X near X naught, then the scalar curvature of G prime should be bounded below by kappa at X naught in this generalized sense, if and only if the same is true for G prime prime. Okay, so this condition looks a little bit technical, but it's actually quite a natural requirement. And one way to see why this is a natural requirement is if we just had, classical smooth Riemannian metrics, what we could do is we could look at the Taylor expansions of G prime and G prime prime at X naught. And if these two metrics satisfied this condition, that would mean that the 0 first and second order coefficients of the Taylor expansion would all agree. So in particular, the 0 first and second derivatives of the metrics at X naught would all be equal. And so the scalar curvatures would be equal. So this is a C0 condition, but it somehow in the smooth case implies that the scalar curvatures are equal. And that's why this is a natural requirement. Okay, and the second one is also a natural requirement. One of the nice properties about the Ricci flow is that it preserves uniform lower scalar curvature bounds. And so this, again, is just saying that if we have an initial metric now that has a uniform lower scalar curvature bound in the generalized sense, then the uniform lower scalar curvature bound should persist under the Ricci flow. Okay, so again, the three things that I want my definition to satisfy are stability under greater than second order perturbation of the metric, preservation of uniform lower scalar curvature bounds under the Ricci flow, and of course, I want my definition to agree with the classical notion for C2 metrics. Okay. All right, so, one thing I have been talking about is that I want to somehow use Ricci flow to define a lower scalar curvature bound for C0 metrics. So I want to somehow take a Ricci flow that is starting from a C0 metric. I haven't explained to you yet what this means. And so that's why, here I say starting from G, but it's in quotes. It's because I owe you an explanation of what it means to have a Ricci flow that starts from C0 initial data. Okay, and if you were starting from smooth initial data, let's say on a closed manifold, what this would mean is that you could find a solution to the Ricci flow equation. And as time goes to 0, then the time slices of the Ricci flow would converge uniformly to the initial data. And also the derivatives of the time slices of the flow would converge uniformly to the derivatives of the initial data. Now, obviously, that doesn't make sense if your initial data is only C0, since it's not going to have derivatives. But you could at least hope that you could find a solution to the Ricci flow that, as time goes to 0, the time slices of the flow converge uniformly to the initial data. Sorry, I should mention, for the rest of this talk, I'll take M to be closed. Compactness is not essential, but it helps with a lot of things. Okay, so, what I'm hoping for is I'm hoping that I can find, for any C0 metric on a closed manifold, I am hoping that I can find a solution to the Ricci flow equation whose time slices converge uniformly to the initial data as t goes to 0. The next result that I'm going to tell you will tell you that actually maybe even this is not quite possible, but at the very least, you will be able to find a solution to the Ricci flow equation that will converge uniformly to the initial data as t goes to 0, modulo pushed forward by a family of diffeomorphisms. Okay, and so here is the result. And there are many results of this type. Okay, so the result is let M be closed and G be a C0 metric on M. Then there exists a time-dependent family of smooth metrics, tilde gt, defined for t in some positive time interval. And there exists a continuous surjection chi from M to M, such that the following two things are true. So first of all, this family of smooth metrics solves the Ricci flow equation. And then second of all, there exists a smooth family of diffeomorphisms chi t from M to M. These are also defined for t in the same positive time interval, such that the chi t converge uniformly to chi as t goes to 0. And moreover, the push forward of the Ricci flow tilde gt by the chi t converges uniformly to g as t goes to 0. Okay, so in other words, if I have any C0 metric on a closed manifold, maybe I can't find a Ricci flow that converges uniformly to G as time goes to 0, but at the very least, I can find a Ricci flow and a family of diffeomorphisms such that after I push forward my Ricci flow by this family of diffeomorphisms, I get something that converges uniformly to the initial C0 metric. Okay, I will say, for people who are more familiar with the Ricci flow, they will maybe recognize this object as the Ricci to Turk flow. The Ricci to Turk flow is actually a fairly well-behaved object. It behaves very nicely analytically, and it sort of satisfies this nice flow equation. So this is not such a, it looks a little bit technical, but this is not such a bad thing. Okay. And so we say that the pair, which is the Ricci flow tilde gt, together with this continuous surjection chi, is a regularizing Ricci flow for G. Okay, and so we use the word regularizing because the Ricci flow is smooth for all positive times, even though the initial data is not smooth. I don't know if chi being a continuous surjection here is the optimal result. And actually, it has been shown recently by Lam and Simon that at least for some metrics on 4 manifolds, we can always take chi to be a homeomorphism. Okay, but I don't know if this is always true. Okay. All right, just a couple more observations about the regularizing Ricci flow. So these diffeomorphisms are relatively well behaved. We can take them to distort points only by square root of t. And then also, in the classical case on closed manifolds, you have uniqueness of the Ricci flow. In this case, we may not have uniqueness necessarily, but we do have uniqueness up to isometry. Okay, so what I mean by that is that if tilde gt prime chi prime is also a regularizing Ricci flow for G, then there exists a diffeomorphism alpha from M to M such that the pullback of tilde gt is equal by alpha is equal to tilde gt prime, and chi precomposed with alpha is equal to chi prime. Okay, so maybe we don't have true uniqueness, but at least we have uniqueness up to smooth isometry. Okay. Okay, so now I have told you what it means to have a Ricci flow starting from C0 initial data. What it means is that you have a solution to the Ricci flow equation, which converges uniformly to the initial data after pushing forward by this family of diffeomorphisms. Since this Ricci flow is going to be smooth for positive times, this gives us kind of a clue about how to use this Ricci flow to define what it means to have a lower scalar curvature bound for the initial data. So specifically, if I want to know whether my C0 initial data satisfies a particular lower scalar curvature bound at a point, what I could do is I could take this Ricci flow and I could check whether for positive times, small positive times, the Ricci flow has a similar lower scalar curvature bound near that point, okay? And so this is how I'm going to define what it means to have a lower scalar curvature bound for a C0 metric at a particular point. I'll break this down. It looks a little bit complicated, but basically all I am doing is I'm looking at the point that I'm interested in, and then I'm running the Ricci flow, which is smooth for positive times, and I'm looking at the scalar curvature of that flow near the point that I'm interested in. Okay. And so, so let me read the definition now. So let M be closed and G a C0 metric on M. For beta between 0 and 1/2, we say that G has scalar curvature bounded below by kappa at x in the beta weak sense, if the following is true. So if there exists tilde gt chi, a regularizing Ricci flow for my metric G, and there exists some point y in the pre-image of x under chi, such that the following is true. So the inf over all c greater than 0, this is not important, but of the lim inf as t goes to 0, the inf of the scalar curvature of the flow at time t on the ball of radius ct to the beta around y. Okay, so here this is a ball of radius slightly larger than square root of t. If this whole quantity is greater than or equal to kappa. Okay, so, to maybe digest this a little bit, okay, we can ignore this infimum over all positive constants. This is just here for scaling purposes. So really, the main thing is that we're taking t going to 0, and we're looking, as t goes to 0, we're looking at the time slices of this regularizing Ricci flow. And then I want to check, what does the scalar curvature of my regularizing Ricci flow look like? And instead of just looking at it at a single point, what I'm going to do is I'm going to look at it in a neighborhood of a particular point. And this neighborhood is going to have size slightly larger than square root of t. Okay, and so here you may wonder, why am I looking at y in the pre-image of x under chi instead of just looking at x, because I'm interested in defining a lower scalar curvature bound at x. And the reason for this, or one way you can sort of understand this, is because the Ricci flow itself does not converge uniformly to the initial data. It only converges uniformly using, after pushing forward by this family of diffeomorphisms. And so somehow this condition is here in order to get rid of this twist by the family of diffeomorphisms. Okay, but so to summarize, basically I want to define what it means for a C0 metric to have a lower scalar curvature bound at a particular point by running this regularizing Ricci flow and then checking as t goes to 0 whether the flow has a similar lower scalar curvature bound in a neighborhood of that point, and the neighborhood is going to have size a little bit larger than square root of t. Okay, so I should mention a couple of things. So, this definition relies on some choices. It relies on a choice of a regularizing Ricci flow for G. And it, since chi is only a continuous surjection, it also relies on a choice of y in the pre-image of x under chi. But actually, this definition is independent of both of these choices. Oh, okay, sorry. This is just something I mentioned earlier. Okay, and so this is my definition, and now I'm just going to remind you of the items that I wanted this definition to satisfy. So first of all, I wanted this definition to be stable under greater than second order perturbation of the metric, greater than second order, in this sense. And I wanted uniform lower scalar curvature bounds to be preserved under the Ricci flow. And so here, when I say a Ricci flow starting from G, what I mean is a regularizing Ricci flow for G. And then last of all, I, of course, want this definition to agree with the usual notion of a lower scalar curvature bound for C2 metrics. Okay, and so this last item is actually like fairly straightforward to check, because if you have, a smooth metric or a C2 metric, you can just take the normal Ricci flow, and this is just going to turn into a normal limit. And so this last one is not hard. The two things that we kind of need to be careful about are these first two items. So first of all, we want to know whether this definition is stable under greater than second order perturbation of the metric. And then we also want to know whether uniform lower scalar curvature bounds are preserved by the regularizing Ricci flow. Okay. Okay, so now I'm going to tell you a theorem, and the consequence of this theorem is that the answer to this, this first question is yes, this item is indeed satisfied. Okay. And so here is this theorem. What it says is the following: let M be closed and G prime and G prime prime be C0 metrics on M that agree to greater than second order around some point X naught. Then there exist regularizing Ricci flows tilde GT prime chi prime and tilde GT prime prime chi prime prime for G prime and G prime prime respectively, such that for beta in this interval, so for some beta smaller than 1/2, if C is any positive constant and T is sufficiently small, depending on C, the scalar curvatures of these two families of metrics that approximate the initial data will stay close. Okay, so more precisely, the supremum on the ball about X naught, a radius C T to the beta, of the scalar curvature of the push forward of the tilde GT prime by chi prime, minus the scalar curvature of the push forward of the tilde GT prime prime by chi prime prime. This quantity is bounded above by CT to the omega, and here omega is some small positive exponent. So in particular, this goes to 0 as T goes to 0. Okay, so this looks a bit technical, but basically all this is saying, recall that these were these nice families of metrics that uniformly approximated my initial data. So this is going to go to G prime as T goes to 0. In C0. And this one is going to go to G prime prime as T goes to 0. C0. Okay, so, this looks a bit technical, but really what this is saying is that if I have two C0 metrics that initially agree to greater than second order at a point, then these smooth families of metrics which approximate them are going to have scalar curvatures that stay very close in a ball of radius T to the beta around that point. Okay, and they stay close like T to some positive power. Okay, so yes, this looks a little bit technical, but if you kind of remember the definition that I showed you on the previous slide and you untangle this result, it will indeed follow, I'll mention that later. It will indeed follow that this first item is satisfied. So if you have two C0 metrics that initially agree to greater than second order, then this generalized lower scalar curvature bound will hold for one at a point X naught, if and only if it holds for the other. Okay. What I was going to mention that I skipped over here is that the way I have stated this, we have two metrics on the same closed manifold, but actually there's a version of this theorem that works if you have two metrics on different manifolds that just agree to greater than second order in some coordinate chart. So this is really a very local statement and doesn't depend on the topology of the manifold. Okay, so far I have shown that if I have two C0 metrics that initially agree to greater than second order in this C0 sense, then these sort of smooth families of metrics that approximate them are going to have scalar curvature that stays close near the point I'm interested in. Okay, and so it follows that this first item is indeed true. Okay, so my definition is, now I have shown my definition is stable under greater than second order perturbation of the metric. And what I want to do now is I want to examine whether uniform lower scalar curvature bounds are indeed preserved under the regularizing Ricci flow. Okay, and so this theorem says that yes, indeed, that is the case. All right, I will read it now. So the theorem says, let M be closed and G a C0 metric on M. Suppose there exists some value of beta in 0 to 1/2, such that the scalar curvature of my C0 metric is bounded below by a constant kappa naught in the beta weak sense everywhere in M. Then if tilde GT is any regularizing Ricci flow for G, the scalar curvature of each time slice of the flow is also going to be bounded below by kappa naught for all T greater than 0. Okay, and so in other words, yes, indeed, the second item is satisfied. So uniform lower scalar curvature bounds are preserved under the regularizing Ricci flow. Okay, just an observation. So one consequence of this theorem is that if I have a C0 metric that satisfies a uniform lower scalar curvature bound in the beta weak sense, then automatically it is going to admit a uniform approximation by smooth metrics that satisfy the lower scalar curvature bound in the classical sense. Okay, and the reason for that is that, okay, any regularizing Ricci flow I have shown in this theorem is going to satisfy the same uniform lower scalar curvature bound. And so if I push forward my regularizing Ricci flow by the sort of appropriate family of diffeomorphisms, I will find a smooth family of metrics that satisfy this classical lower scalar curvature bound and converges uniformly to the initial data. Okay, and so, to summarize, if I have a C0 metric which satisfies this uniform lower scalar curvature bound in the beta weak sense, then you can find a smooth family of metrics that uniformly approximates it, and the smooth family of metrics satisfies the lower bound in the classical sense. Okay. And so in particular, in the case of uniform lower bounds, the beta weak definition implies Gromoff's polyhedron definition. And this is because Gromoff's polyhedron definition holds for all smooth metrics with the classical lower bound, and it's closed in C0. Okay, but somehow this is kind of a sleight of hand because we're using this this characterization involving a uniform approximation by smooth family of metrics. And so in particular in the converse, I don't know. So even in the case of uniform lower bounds, my question is, does Gromoff's polyhedron definition imply this beta weak definition? And then, of course, really, I was interested originally in the case of pointwise lower scalar curvature bounds. And in this setting, less is understood. So the question is totally open. In the pointwise case, do we have a lower scalar curvature bound? There should be quotes. Well, in the beta weak sense, if and only if we have one in the sense of Gromoff. Okay, so these are some questions I would like to know the answer to. Okay, what did I want to talk about next? Okay, this is a little bit of heavy machinery. I think maybe I can skip over this. But, I just wanted to talk about how, I've been kind of emphasizing how I wanted to come up with a pointwise lower bound, and the pointwise case is kind of subtle. But even in the case of uniform lower scalar curvature bounds, you can obtain some kind of interesting results, by thinking of lower scalar curvature bounds in terms of Ricci flow in this way. And so in particular, we can address this question. And so the question was posed by Gromoff in 2014. And the question is, let G be a continuous Riemannian metric on a closed manifold M, which admits a C0 approximation by smooth Riemannian metrics GI, such that each GI has almost non-negative scalar curvature. So it has scalar curvature bounded below by minus epsilon I, where this goes to 0 as I goes to infinity. Okay, and so the question is, does M admit a smooth metric of non-negative scalar curvature? And what one can show is that actually G is going to have non-negative scalar curvature everywhere in the beta weak sense. So in particular, any regularizing Ricci flow is going to have non-negative scalar curvature, and the regularizing Ricci flow is smooth for positive times. So actually we'll have an entire family of smooth metrics that have non-negative scalar curvature. And after we push forward that family of metrics by the appropriate family of diffeomorphisms, we will have a smooth family of metrics of non-negative scalar curvature that converge uniformly to G. Okay, and so the answer is yes. Moreover, G admits a uniform approximation by smooth metrics of non-negative scalar curvature. Okay, so, as I said, my focus was just kind of on the pointwise case, but I wanted to just bring this up because I think even in the case of uniform lower bounds, there are some interesting things that can be proven using Ricci flow in this setting. Okay, yeah, so, I've kind of told you the central results of this theory. I've told you my definition. And what I want to do now is kind of review some of those results and then explain a little bit about how to prove them. Okay. And so, the first thing I want to talk about is how to prove the existence of a regularizing Ricci flow, right? Because, previously we didn't really know what it meant to have a Ricci flow starting from C0 initial data. And so I need to explain to you how I construct such a flow. Okay, and so, so this theorem is in brown because I'm reminding you that this is this lemma because I'm, reminding you of this statement that you've already seen. This is the statement that explains in what sense there exists a Ricci flow starting from C0 initial data. Okay. And so, yes, just as a reminder, what it means is that you have a Ricci flow which converges uniformly to the initial data after pushing forward by an appropriate family of diffeomorphisms. Okay. And so, what we are trying to do is find a solution to the Ricci flow equation that somehow corresponds to the initial data. And actually, this is kind of a tricky thing to do, even in the case of smooth initial data, because, even in the case of smooth initial data, one thing that you need to contend with is the fact that the Ricci flow equation is not strongly parabolic, and it would be kind of nice if it were strongly parabolic, because then you would expect to have a nice smooth, short time solution because of parabolic existence theory, but it's not strongly parabolic. And so usually what we do to get around this is this trick of de Turk, which is that we first solve a kind of a related equation that is strongly parabolic, and then after you solve this related equation, you can pull this related equation, the solution to this related equation back by some family of diffeomorphisms to get a Ricci flow. Okay, and so this is the related equation that we solve. This is the Ricci de Turk equation. And so, I agree that somehow this doesn't look like it would be much easier to solve than the Ricci flow equation, but actually we choose this vector field X so that this somehow is easier to solve than the Ricci flow equation. And then if you happen to have a solution to this equation, the Ricci de Turk equation, then you can just check that if you pull back a solution to this by the family of diffeomorphisms generated by this vector field X, then the thing that you obtain will be a solution to the Ricci flow. Okay, so really, the tricky part is to figure out whether there is a solution to this equation, and you'll do this however you like. And then once you have that solution, then it's, reasonably easy to turn it into a Ricci flow. Okay, and so you can do this in the smooth case. Since we're starting from C0 initial data, what we need to establish is whether or not it is possible to solve this equation with smooth initial data. Okay, and so this is actually quite a well-studied problem. And I think the first person to study this in 2002 was Miles Simon. And then more recently, Cohen Lamb have some papers on this from 2012 and 2015. They use a somewhat different method. And then I also looked into this, and I showed that the Cohen Lamb method also works on general manifolds. And the upshot of all of these results is that if you have C0 initial data, then you can find a smooth short time solution to the Ricci de Turk flow that converges uniformly to the initial data on closed manifolds. Okay, and so what these results tell us is that if I have any C0 metric, I can solve the Ricci de Turk flow for a short time to get something that converges uniformly to the initial data as t goes to 0. And then, as I explained before, I can pull back that solution by the family of diffeomorphisms generated by this vector field X. And then that's going to give me a solution to the Ricci flow equation. Okay, and so that is the reason that there are diffeomorphisms in this statement. So this thing is precisely the Ricci de Turk flow, which by this result we know converges uniformly to the initial data. And so these diffeomorphisms are precisely those diffeomorphisms that are going to be generated by this vector field X. Now, I guess maybe I can address why there is this continuous surjection chi. Like in the classical case, we don't have this chi running around. And the reason for that basically is that we pull back by this family of diffeomorphisms that is generated by this vector field X. Now, ordinarily, you would, to do this, you would solve an ODE to get the family of diffeomorphisms, and you would solve the ODE subject to the initial condition that the initial diffeomorphism should be the identity. Now, because we have singular initial data, it's not possible to prescribe any initial data at time 0. So what we instead do is that we prescribe the initial data. It's not really initial data. We prescribe some piece of data at slightly positive times. And so somehow this chi is an artifact of the fact that you can't put any initial data at time 0. All right, so this is how we construct a regularizing Ricci flow. Is first we solve a Ricci de Turk flow, and we have a result like this that tells us that it's possible, and then we pull it back by some family of diffeomorphisms to get the regularizing Ricci flow. What I want to do now is talk a little bit about this proof of Cohen Lamb to construct a Ricci de Turk flow for C0 initial data. And the reason I want to talk about it is it's actually sort of relevant for us when we examine the stability of the definition under greater than second order perturbation of the metric. Okay, and so Basically what they do, so they construct a Ricci de Turk flow starting from C0 initial data, and they use some kind of fixed point argument to do this. And so, maybe this is a little bit too much details, but what they do is they study this perturbation equation. This is some smooth background metric, and they kind of use this integral expression for a solution to the Ricci de Turk equation. They use some heat kernel estimates, and they show that a solution to the Ricci de Turk flow is going to arise as a fixed point of this operator, this integral operator. And then they show, for certain initial data on certain Banach spaces, this operator is a contraction mapping, and so it's going to have a fixed point. Okay, maybe that's a little bit too much detail. But anyway, in the course of showing that, they show a result that looks like this. Okay, and so what this is saying, I think this is very interesting. So what this is saying is that if you initially have some piece of initial data, G0, which is close to some background metric, bar G, then for positive times, the Ricci de Turk flow is going to stay close to that background metric in the sense of this X norm. Okay, so this is the X norm. The part for us that's really interesting about this X norm is that it has this sort of local L infinity part. Okay, and so the reason that this result is so interesting for us is because we want to show that our definition is stable under greater than second order perturbation of the metric. Okay, and so, really what this was, remember this theorem, is what we wanted to show is if we have two C0 metrics, so these are going to be pieces of initial data for my Ricci de Turk flow, and if these two metrics are close, not just close in C0, but actually close in the sense that they agree to greater than second order at a point, what I want to show is that their flows stay close, okay, for small positive times, and I want to show that they stay close in the sense that, their scalar curvatures stay close. Okay, and let me just remind you, these push forwards were the Ricci de Turk flows. Okay, so to summarize, I want to have some kind of result that says, if my two pieces of initial data initially agree to greater than second order, so they're very, very, very close at X naught or around X naught, then their Ricci de Turk flows are going to stay very close around X naught, and they're going to stay very close in the sense that their scalar curvatures are going to stay close. Okay. And to compare that with this result, this is saying that if you initially have closeness to some background metric, that closeness will be preserved. Okay, and so what I could do now is if I want to prove this result, what I could do is sort of, okay, well, they have some piece of initial data which is close to some background metric. I have two pieces of initial data which, start out very close. And they are not just close in the sense that they're close in C0, but they're actually close in the sense that they agree to greater than second order. And so what I can do is I can put some weight onto this C0 norm, which reflects the fact that they initially agree to greater than second order. And actually, I'll need to pick up something finite, but that doesn't matter. And so how do I want to draw this? Okay, so, if initially I have my two metrics that agree to greater than second order around a point, then it means that their difference, near that point looks kind of like this. Okay, so this is the point X naught, and this, this graph looks like d to the 2 plus eta x naught. Okay, and so what I'm going to weight by here is basically 1 divided by this picture. So this weight blows up at X naught, except for the fact that these agree to say greater than second order. And now what I want to show, hopefully using a method similar to that of Koch and Lamb, is I want to show that somehow these two metrics give rise to Ricci de Turk flows that stay close. Okay, so I'm going to replace GT and the background metric with my two Ricci de Turk flows that I'm interested in. And I want to show that these stay close. Okay, and so somehow, I'm going to prove some kind of weighted estimate. I have a weight over here, and I want to know what's going to happen to this weight as time goes on. Now, the weight looks like 1 divided by this picture. If I were to evolve this picture by something parabolic, like the heat equation, which the Ricci de Turk flow is, then what would happen is that this picture, in this region, it would pull in some heat from out here. Okay, and so in this region, it's going to rise up a little bit. And the amount that it will rise up is at time t, it will rise up by square root of t. Okay, and so I'm going to weaken my weight a little bit by including this square root of t. Okay. And this should be T2. Okay, and so if I, sort of put weights onto these norms of Cohen-Lamb, I can do a weighted version of their argument. And I will find that if I initially had, two metrics that agree to greater than second order so that this right-hand side is finite, then their Ricci to Turk flows are going to continue to almost agree to greater than second order. They're going to be close in the sense that this weighted term is finite. Okay, so these almost agree to greater than second order, but they have this extra square root of t. Okay, and so what this is telling you is that initially you have two metrics that are close, to second order in the C0 sense, and this is telling you that their Ricci to Turk flows are going to stay close in this, sort of weighted C0 sense. And then actually, once you have this weighted C0 estimate, it's not so hard to turn that into an estimate on the scalar curvatures. Okay, so basically the idea behind proving this theorem is to somehow put these weights onto the norms of Cohen-Lamb and try to make a weighted version of their argument. Okay. And then the last thing I wanted to talk about is how do we prove this statement about uniform lower scalar curvature bounds? Okay, so remember, this is the theorem that says that if initially you have a uniform lower scalar curvature bound in the beta weak sense, then for any regularizing Ricci flow for all positive times, that Ricci flow is going to have the same lower scalar curvature bound in the classical sense. Okay, and so how do I prove this? Okay, so I think, it's enlightening to see this proof because it explains, the significance of beta in this range. Now, my suspicion is that beta can always be replaced with 1/2, but somehow this proof does not work in that case. Okay, so we're going to see where this beta appears. And so let me just remind you of the definition. Okay, so this theorem is saying that if this condition holds everywhere initially for some constant kappa naught, then for any regularizing Ricci flow, the time slices of the regularizing Ricci flow are also going to have scalar curvature bounded below by kappa naught. Okay. And so how would I prove this? Well, I'm going to prove it by contradiction. Let's just do it for kappa naught equals 0. So what I'm going to do is I'm going to argue as follows. So suppose I have, some positive time at which this theorem is false. So I have some point and some positive time such that the scalar curvature is actually negative. And what I will do is I will use the evolution of the scalar curvature under Ricci flow. So this is where we're using these nice properties of the Ricci flow. I will use the evolution of the scalar curvature under the Ricci flow to show that if this were the case, then at time t/2, at a nearby point, I also had to have a scalar curvature that was almost as negative. Okay, and then again, I can sort of repeat this argument. And when I repeat this argument, what I can do is I can find a sequence of points that are all very close to one another, and I can find a sequence of times going to 0, such that the scalar curvature at all of these points at the corresponding times is always bounded away from 0. And, and then it would follow that this condition actually had to have failed somewhere. Okay, so this is a sort of high level, explanation of this argument. Let me maybe make this a little bit more precise. So what I'm going to do, as I said, is I'm going to suppose we have some point x and some positive time t such that the scalar curvature is negative. And I want to show that at time t/2, the scalar curvature is almost as negative in the ball of radius x around t to the beta. Okay, so the beta is here because that's basically the amount that these points are allowed to diverge. Okay, so suppose we have this negative point at a positive time, and suppose that at an earlier time t/2, actually we had a reasonable lower bound on the scalar curvature on this ball of radius t to the beta around x. Okay, so I've left a blank space here because I'm going to lose something. And so now what I'm going to do is I'm going to use the fact that the scalar curvature is a super solution to the heat equation under Ricci flow. And so, if I want to lower bound my scalar curvature at x at the time t, I can do that by integrating the scalar curvature at time t/2 against a heat kernel. Okay, so this is my hypothesis. It's this, or I guess my contradiction assumption. And then I'm going to lower bound my scalar curvature at x at time t by integrating the scalar curvature at time t/2 against a heat kernel based at x. And the reason I can do this is because of this evolution equation. Okay, so this is the nice property of the Ricci flow coming into play. Okay, and so when I integrate my scalar curvature at time t/2 against the heat kernel, I can integrate it against the heat kernel within the ball of radius t to the beta around x. And I can also integrate it outside of the ball of radius t to the beta around x. Okay, so this is not surprising. I'm just splitting up this integral over the whole manifold, and I'm going to treat these two parts separately. So, my contradiction assumption here was that the scalar curvature had a nice lower bound in this ball of radius t to the beta about x. Okay, and so in this region, we have this lower bound minus epsilon plus blank. Okay, and blank is something that I'll fill in later. And then outside of this ball, the scalar curvature could be very negative. Okay, it could be as bad as minus some constant over t. But on the other hand, outside of this ball, because this is a ball of radius t to the beta, and beta is strictly smaller than 1/2, the heat kernel is going to decay very quickly, okay, because we have these exponential heat kernel estimates. And since we're integrating outside this ball of radius t to the beta, we'll get some term that decays exponentially. Okay, and so in order to get a contradiction, I just need to fill in this blank with c over t. Something to cancel out this term. And sorry, one of these should be a strict inequality. And so what I have done is I have used heat kernel estimates, these heat kernel estimates, the exponential heat kernel estimates, to show that if indeed I have a point at positive time that has negative scalar curvature, then actually at time t/2, there had to be a point within t to the beta of my first point that had scalar curvature that was almost as negative. Okay, so this should have scalar curvature now bounded above by minus epsilon plus some loss that decays exponentially. Okay, and so what I could do is I could iterate this process, and because this loss decays exponentially, it's not going to cause any problems. And what I will find is that even as t goes to 0, I will be able to find the sequence of points that are all very close to one another that always have scalar curvature bounded above, by minus epsilon over 2. Okay, and so in particular, okay, I'm just summarizing now. The heat kernel estimates tell me I can find a sequence of points xk such that the scalar curvature at xk at the time t/2 to the k is always going to be bounded above by minus epsilon over 2. And moreover, all these xk are, within this ball are in this ball around x infinity. Okay, so all these xk are in the ball of radius c times t/2 to the k to the beta, so the beta ball of x infinity. And so it follows that this condition could not be true at x infinity, because in all of these balls, you can find a point where the scalar curvature is actually negative and bounded above by minus epsilon over 2. Okay, so this is where we see the significance of the beta is because we need these sort of exponentially decaying heat kernel estimates. Okay, that was all I had planned to say. Sorry, I think I went a little bit fast, but if people want to discuss a little more, I'm happy to do that.